Okay, related rates. Related rates are tough problems. We will always be trying to relate one derivative to another derivative. That's why these are called related rates. We're trying to write a relationship between two derivatives. And typically we're trying to solve for one of those derivatives at a particular moment in time. Now, the way most of these are set up is we'll have a couple of different variables in the problem. We'll figure out some way to relate those variables. We'll find some equation. Maybe our variables will be volume and radius. And we'll write down the formula for volume of a sphere. And then both of those variables are changing, usually with respect to time. Our independent variable is almost always time in related rates problems. So all of our dependent variables are changing with respect to time. So we'll be trying to relate their derivatives with respect to time and figure out how quickly our volume is changing at a particular moment in time. Okay, so let's look at one example here that doesn't have any words in it. It's just mathy. So I've got some relationship between X and Y. In a wordy problem, I would have to figure out this relationship. It wouldn't just be handed to me. I want to find how quickly Y is changing with respect to time at a particular moment, at that moment right there, when X equals 1. Now, when I say at a particular moment, I'm not telling you the time. I didn't say T equals 3 seconds, but I told you some information about that time. Whatever time it is when X equals 1. Okay, so we have some relationship between X and Y. I'm just going to write down my function that I have here. Oops. X squared plus 3. I want dy dt when at the particular moment X is equal to 1. I don't know the time. So that's at some time. I'm never even going to find that time. I don't really care what my clock says at that moment, but I know that at that moment, X is equal to 1. And I'm also told that at that moment, or maybe even all the time, for all times, that X is changing at a rate of 4 units per time unit. So X and Y are both dependent on time here. T is my independent variable, and I have 2 dependent variables. So what I'm going to do is I want to relate these 2 rates. That's why these are called related rate problems. I want a relationship between dy dt and dx dt. And however I can come up with that relationship is good. Sometimes there's more than one way. Sometimes there are a bunch of different ways to find that relationship. In this case, there won't be. There will only be one. But just somehow, we got to come up with a relationship between dy dt and dx dt. Okay, so the way we're going to do that in this case is take the derivative with respect to time. Take d dt of both sides. And this is pretty much what you're going to do every single time. You're going to take the derivative with respect, and it's almost always time, of both sides. Implicitly, we're using implicit differentiation. Okay, so taking the derivative of y with respect to t is dy dt. And I'm not going to use any prime notation here. I'm going to do this all with Leibniz notation. Equals derivative of 2x with respect, here's where people get messed up. I'm not taking the derivative with respect to x. I'm taking the derivative with respect to t. X is a function of t. I've got some function squared there. The derivative of junk squared is 2 times junk times the derivative of what's inside. That's my inside, x. The derivative of x with respect to t is just dx dt. Plus, and then derivative of 3 is just 0. With respect to anything, it's a constant. Okay, so I want this at a particular moment. When x equals 1. And this is, I'm told that x is changing with respect to time at a rate of 4 units per second, or whatever t is measured in. So I'm going to plug in the 1 for my x, the 4 for my dx dt, so dy dt, and I'm going to write here at the moment when x equals 1 will be 2 times 1 times 4, 8. So every problem is going to be like this. We're going to have some word problem. Our first goal is to write some equation that relates all of our variables. And obviously it's got to be a true equation. We can't just make up an equation, but it's got to be some true relationship between our variables. Then we take the derivative with almost always with respect to time of both sides to relate the derivatives. And then we just plug in all of our givens. Sometimes we got to do a little more algebra, but we're almost always solving for the derivative of one of the variables at a particular moment. And notice here, I'm going to keep saying this, I never found the time. I don't know what the clock says when x equals 1, but that's one particular moment in time when x equals 1, the y is changing at this rate. Okay, that's a good place to stop on that one.